Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The discovery of superconductivity by Heike Kamerlingh-Onnes in 1911 presented the world of physics with a phenomenon as profound as it was perplexing. In his Leiden laboratory, the abrupt disappearance of electrical resistance in mercury below a critical temperature of approximately 4 Kelvin suggested the existence of a perfect conductor, a state of matter seemingly defying the established principles of electron scattering in metals. This initial wonder deepened 2 decades later with the work of Walter Meissner and Robert Ochsenfeld, who demonstrated that superconductors also expel magnetic fields, a property known as perfect diamagnetism. This Meissner effect revealed that superconductivity was a true thermodynamic equilibrium state, a distinct phase of matter with unique properties, and something far more fundamental than an idealized classical conductor. For nearly 50 years, the problem languished, a grand challenge that resisted the formidable intellects of the era. The world's foremost theorists offered proposals, yet each one failed to capture the essence of the phenomenon. It was a puzzle of the highest order, waiting a conceptual breakthrough that could unite the disparate clues into a coherent microscopic theory. That breakthrough arrived in 1957, in a seminal paper published in Physical Review by John Bardeen, Leon M. Cooper, and John Robert Schrieffer. Their theory of superconductivity, now universally known as the BCS theory, was a monumental intellectual achievement, a triumph of man-body quantum mechanics that provided a complete and elegant explanation for this half-century-old myth. The path toward the BCS theory was paved with crucial experimental observations that gradually constrained the vast space of theoretical possibilities. The phenomenological equations developed by Fritz and Heinz London in 1935 offered a powerful macroscopic description of the zero resistance and the Meissner effect, postulating a new relationship between the supercurrent and the vector potential. The London theory worked remarkably well, yet it was an ad hoc construct, a brilliant piece of physical intuition without a microscopic foundation. It described what happened without explaining why. The most decisive clue, the veritable Rosetta Stone for the problem, emerged in 1950. Experiments by Emmanuel Maxwell and, independently, by group including C. A. Reynolds, revealed the isotope effect. They showed that the critical temperature of a superconductor depended on the mass of its constituent ions. Specifically, the critical temperature was inversely proportional to the square root of the isotopic mass. This finding was a thunderclap in the community, for it unequivocally implicated the crystal lattice in the mechanism of superconductivity. The motion of the massive ions, the very vibrations that cause electrical resistance in normal metals, was somehow essential to its complete absence in the superconducting state. This pointed directly to the electron-phonon interaction, the coupling between the conducting electrons and the quantized lattice vibrations, or phonons, as the central piece of the puzzle. The problem was longer one of pure electronic behavior. It was a complex dance between electrons and the lattice in which they moved. It was this critical insight that John Bardeen, already a Nobel laureate for his convention of the transistor, seized upon at the University of Illinois. He assembled a small group to attack the problem, which included the young postdoctoral researcher Leon Cooper and the graduate student John Robert Schrieffer. The first pivotal piece of the solution came from Cooper. In 1956, he considered a simplified, yet highly illuminating, problem. He analyzed the behavior of 2 electrons added to metal at absolute zero, just above the surface of the filled sea of electrons known as the Fermi sea. In a vacuum, 2 electrons repel each other via the Coulomb force. Within the metallic lattice, however, the situation changes. An electron moving through the crystal attracts the positive ions, causing a slight, localized deformation of the lattice, a ripple of concentrated positive charge. This deformation propagates as a phonon. A second electron, moving through this polarized region, and be attracted to this excess positive charge. This phonon-mediate attraction can, under the right conditions, overwhelm the direct Coulomb repulsion between the electrons. Cooper's calculation produced a stunning result. He demonstrated that for an arbitrarily weak net attractive interaction, 2 electrons with opposite momenta and spins, near the Fermi surface, would form a bound state. This bound pair, the Cooper pair, possesses a lower total energy than 2 free electrons. The Fermi sea, once believed to be the ground state of a metal, was in fact unstable against the formation of such. Cooper's work established the fundamental ingredient of the theory, the pairing of electrons. Yet a profound challenge remained. His analysis concerned a single pair of electrons in isolation. A real metal contains a vast number of electrons, approximately 10 to the power of 23 per cubic centimeter, all interacting simultaneously. The problem was to construct a man-body ground state for the entire system, a wave function that could describe a condensate of these overlapping Cooper pairs. Bardeen and Cooper struggled with this for months. The solution came in a moment of inspiration to the junior member of the team, John Robert Schrieffer. Famously, the idea struck him while riding the New York City subway in early 1957. He realized that the correct approach was a variational one, constructing a trial wave function whose energy could be minimized. The resulting BCS ground state wave function is one of the most celebrated constructs in modern physics. It is a coherent quantum superposition of all the electrons in the system, but with a specific structure. The wave function pairs every electron with momentum k and spin up with another electron of momentum minus k and spin down. The state is a vast, intricate product over all possible momentum states, where each term in the product is a linear combination of the state being empty and the state being occupied by a Cooper pair. This formulation elegantly handles the immense complexity of the matter-body problem, creating a state that is lower in energy than the normal metallic state. The Cooper pairs within this macroscopic quantum state are interlocked and highly correlated. The spatial extent of a single pair is typically hundreds of nanometers, and distance far greater than the average spacing between electrons, meaning each pair overlaps with millions of others. This collective, vis-coherent fluid of electron pairs is the microscopic essence of the superconducting. From this sophisticated wave function, the major experimental signatures of superconductivity emerge as natural consequences. The most significant prediction of the BCS theory is the existence of an energy gap in the electronic excitation spectrum. In the normal state, there is a continuum of available energy levels, allowing electrons to be scattered with an arbitrarily small energy transfer. In the BCS state, the binding of electrons into Cooper pairs opens a finite energy gap, commonly denoted by the Greek letter delta, separating the ground state from the first excited states. To create an excitation, one must break a Cooper pair, a process that requires a minimum energy of 2 delta. This energy gap is the key to understanding the remarkable properties of superconductors. It explains the phenomenon of zero resistance with profound clarity. For a current to dissipate energy, electrons must scatter, moving from one quantum state to another. In the BCS state, such scattering is forbidden unless the energy supplied by collision is sufficient to overcome the gap and break a pair. For small electric fields and currents, the electrons, locked in their collective head state, flow without any possible mechanism for dissipation. The theory also provides a microscopic derivation of the Meissner effect, showing how the macroscopic quantum coherence of the ground state allows shielding currents to form spontaneously to expel an external magnetic field. Furthermore, the BCS theory quantitatively predicted thermodynamic properties. It correctly described the exponential suppression of the electronic specific heat, low temperatures, a direct consequence of the energy gap, and accurately predicted the magnitude of the sharp jump in specific heat observed at the critical transition temperature. Crucially, the theory gave a full account of the isotope effect. The expression for the critical temperature, T sub c, derived from the theory, is proportional to the Debye frequency of the lattice vibrations, which in turn is proportional to the inverse square root of the ionic mass. A key equation from the theory states that the critical temperature is approximately proportional to the Debye temperature multiplied by the exponential of -1 divided by the product of the density of states at the Fermi level and the electron-phonon interaction potential. This beautifully connected the macroscopic transition temperature to the microscopic parameters of the metal, solving the central puzzle posed by the 1950 experiments. The publication of the theory in 1957 was met with immediate and widespread acclaim. It was a complete and stunningly successful solution to one of the longest-standing problems in physics. Independent work by N. Orgolybov in the Soviet Union, using a different mathematical formalism involving canonical transformations, arrived at similar physical conclusions, powerfully reinforcing the correctness of the BCS picture. The theory's influence radiated outwards, solidifying the foundations of condensed matter physics and inspiring developments in other fields. It provided the microscopic justification for the phenomenological Ginzburg-Landau theory, with the Ginzburg-Landau order parameter finding its physical identity in a BCS energy gap parameter. In 1962, Brian Josephson, then a graduate student at Cambridge, used the BCS framework to predict that Cooper pairs could quantum mechanically tunnel through a thin insulating barrier separating two superconductors, a phenomenon now known as the Josephson effect. Its experimental confirmation provided dramatic evidence for the macroscopic quantum coherence of the BCS ground state and launched the field of superconducting electronics. The conceptual power of the BCS model transcended its original domain. The idea of a ground state condensate arising from particle pairing, resulting in spontaneous symmetry breaking and the opening of an energy gap, proved to be a profoundly fertile concept. Iwakiro Nambu and Giovanni Jonah Lacinio applied a similar mathematical structure to the physics of elementary particles, developing a model of chiral symmetry breaking in quantum cryptodynamics which served as an important conceptual forerunner to the modern understanding of mass generation via the Higgs mechanism. Of course, the history of science is one of continual refinement. The original BCS theory, in its simple form, describes conventional superconductors where the pairing glue is provided by phonons. The discovery of high-temperature cuprate superconductors in 1986, followed by other families of so-called unconventional superconductors, revealed materials where the critical temperatures were far too high to be explained by the simple electron-phonon mechanism. These discoveries showed that other interactions, such as magnetic spin fluctuations, could also serve as the pairing glue. The BCS paradigm of forming bound pairs to create a gapped, coherent ground state remains the central organizing principle, but the search for the specific pairing mechanism in these exotic materials constitutes one of the most active and challenging frontiers in modern physics. In conclusion, the theory of superconductivity, developed by John Bardeen, Leon N. Cooper, and John Robert Schrieffer, stands as a paramount achievement of 20th century science. It represents a tour de force of theoretical physics, demonstrating the power of quantum mechanics to explain emergent phenomena in complex man-body systems. With extraordinary elegance and predictive power, it wove together the disparate experimental threads of zero resistance, a Meissner effect, and the isotope effect into a single, unified microscopic tapestry. The theory solved a deep and persistent mystery that had occupied the field for nearly 5 decades. Its legacy endures, serving as the bedrock of our understanding of conventional superconductivity and as the essential framework for exploring the frontiers of new quantum materials. More broadly, the conceptual innovations of pairing, spontaneous symmetry breaking, and the energy gap have become part of the fundamental toolkit of theoretical physics, a testament to the profound and lasting impact of an idea born from a flash of insight in the New York City subway. The BCS theory is a story of persistent inquiry, crucial clues, and brilliant theoretical synthesis, culminating in a complete picture of one of nature's most remarkable collective quantum states.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.